Hi students. So in this session we are going to be discuss about floating point numbers and its operations. So generally there are two basic data types implement in the computer system. There are two basic data types that we can implement in a computer system. So the first one is fixed point numbers. So all the integers we can represent with a fixed point numbers. The second one is floating point numbers. So now we will describe about the floating point numbers. So in generally, whenever you consider a floating point number, it includes all integer values as a fractional values. So whenever you take a value as a 1.5, one is an integer value and the second one is a fractional value. So that means, so generally we will call that one as a real numbers also. So real value. So that means whenever you consider that the floating point value. So the floating point value which will consist of some integer part as well as it also will consist of some fractional part also. The floating point representation includes three fields. If you consider any floating point value, it will consist of three fields. One is a sign bit field, the second one is exponent field, and the third one is fractional Montesa. These are the three bits it will consist of. So whenever you go for that, let us consider one example. 111.100001110. So after this we can write the total value as 1.11100001110 into 2 power 5. Here 1 is a sign bit and the remaining part is a Montesa and exponent value 2 power something, we will have an exponent value. So whenever you go for this one, we will use an IEEE standard format for floating point numbers. So whenever you go for this one in the IEEE format, there are two ways to represent an IEEE standard format. One is called as a single precision format and the second one is called as a double precision format. Whenever you go for the single precision format, so it will use a 32-bit standard. The single precision format will use a 32-bit standard. Whenever you go for a double precision representation or a format, it will use a 64-bit standard. So that means 64 bits will be there in a double precision and 32 bits will be there in a single precision. So coming to the single precision format, the single precision representation occupies a single 32-bit word. The scale factor has a range of 2 power minus 26 to 2 power 126 to 2 power plus 127, which is approximately equal to 10 power plus 38. The 32-bit word is divided into three fields. So that is one bit is a sign bit that occupies one bit. Sign bit is 1, exponent is 28 bits and Montesa is 23 bits. So here the total 32. See, 1 bit for sign, 8 bits for exponent value and 23 bits for Montesa value. 1 plus 8 9, 9 plus 23 32. Signed exponent E. An unsigned exponent E dash equals to E plus 127, thus E dash is in the range 0 to in between 225. The last 23 bits represents Montesa. Since binary normalization is used, the MSB of the Montesa is always equal to 1. So the last 23 bits represents the Montesa. Since binary normalization is used, the MSB of the Montesa is always equal to 1. So always the M represents a fractional part. The 24-bit Montesa provides a precision equivalent to about 7 decimal digits. Coming to the second double precision format. So whenever you go for the 64 bits, so whenever you go for the 64 bits, So here also 1 bit as a sign bit and 1 bit as a sign bit and 11 bits as the exponent and 52 bits as a Mantua fraction. See, the 64-bit representation, 1 bit for sign and 11 bits for exponent value and 52 bits for Mantua fraction. So here they are using for exponent XS 1023 code. So here the double precision format occupies 60-bit code and it is code and E dash is in the range 1 less than 246. A 53 Mantua provides a precision equivalent to about 16 decimal digits. So whenever you go for this one, the floating point numbers, and whenever you go for this one, see how they are going to be represented. So here this is the single precision format. So whenever you consider a single precision format, totally it is 32 bits length. It is totally 32 bits length. So whenever you go for this totally 32 bit length, one bit is called as a signed bit S. So that is 0 is signifies plus and 1 signifies minus. If this bit is 0, then the value is plus value. If the bit is 1, the value is minus value. Here exponent 8-bit sign exponent in excess 127 representation. Whenever they are representing an exponent format here, they are using an excess 127 representation and 23-bit Mantua fraction. Value represented plus or minus 1 point m into 2 power e dash minus 127. This is called as a single precision format. So whenever you go for one example here, so the value represented here is 1.001 dash dash 0 into 2 power minus 87. So that has been represented as a positive value. So that is 0, 0, 0, 1, 1, 0, 0, like that they are example of single precision number. Because of it is a positive value and the sign bit is a 0. Coming to the double precision format, it takes 64-bit length. Whenever it takes a 64-bit length, so at that time the sign bit is going to be used as a 1 bit it is going to be taken and 11 bits for exponent. Whenever it takes 11 bits for exponent, so it is taking XS 1023 code and 52 bit for Mantua representation. So here whenever you the value represented here is in this fashion, we can do that one. So whenever you are representing this particular format, definitely we want to follow the thing. And also whenever you are representing this one, here also normalization condition will be taken here. So in the floating point representation, in the normalization condition, we have a overflow and underflow. So simply we consider the procedure for normalizing a floating point number is how we will do means if MSB of Mantua is equal to 1, shift the Mantua left or right, decrement or increment the exponent by 1 and do. So that means whenever you go for this normalization procedure, so first they will check the MSB unit of Mantua is equal to 1 or not. If it is 1, shift the Mantua left or right. So decrement or increment the exponent by 1. So and do. In this fashion, they are going to be do the normalization of floating point values. So like that here, this is the fundamental concepts of floating point numbers. Just we will see some problems later on. How the problems we can perform on this particular one. So already you have seen this one in the DLD also. How the floating point numbers will be represented. Simply only the thing is you want to say that we have two standards so far IEEE standards. So that is one is a single precision format, so which occupies a 32 bits. So within that 1 bit for sign, 8 bits for exponent and 23 bits for Montesa. In the double precision format, double of that one, it also requires 64 bits, 1 bit for sign, 11 bits for a representing of exponent, and 52 bits for representing a Montesa. Like this, the double precision format is going to be represented. Thank you.